Good morning. I'm Graham Rogerson. I'm head of Net Zero Technologies at the Centre. Great to have you here this morning. This is our Tech20 series. I've been speaking to a few of you. I think you've been here before, but you know the script. This is the Centre's social showcase for technology and some of our projects that we've got on the go. So great to have you here. Format is 20 minutes of social that we just had. 20 minutes of presentation. We've got Ken online this morning, and then 20 minutes of Q&A that I can facilitate. So I'll let you give you a quick read of this one. Hopefully this all makes sense. Kind of piece. Main thing to highlight is the toilets downstairs this morning are out of action. If you need the restrooms, there's some on the floor above. Just wander up there. For the fire exit, so anything happens, we're not expecting any drills this morning. We're straight out this door behind us in the corner. You follow people with lanyards, and we muster a couple of doors down outside the dentist. So hope all that makes sense. Robots for our net zero future. So the background to this actually is a government-led Innovate UK programme, Robots for a Safer World. This programme ran from 2017 to 22. It was about taking humans out of extreme environments. Over 100 million pumped into different projects through that programme, which has been great. The centre here, we teamed up with the MOD, the Royal Navy, and Innovate UK to run a specific subsea programme as part of that Robots for a Safer World. It kicked off through COVID, so it was quite challenging, quite different. And 3 projects came out the back end of it, all to do with longer duration or autonomous subsea operations and technology. And that's when I first met Ken, who we're going to hear from today. The weird thing is, Ken and I haven't met in person. We've just been digitally connected. But Ken, nice to see you this morning. Buddy, would you like to quickly introduce yourself, please?
Yeah, sure thing. And yeah, nice to see you again, Graham. So I'm founder and CEO of Autonomous Devices. And yeah, just really pleased to be able to present to you guys today.
Brilliant. Thanks, Ken. Okay, hey, without further ado, we'll start the clock and pass over to yourself, Ken. Take it away.
Great. Okay, fantastic. Thanks very much. So thanks, Graham. So as I said, I'm Ken Wahren, founder and CEO, Autonomous Devices. Autonomous Devices specializes in advanced robotic applications for really harsh and challenging environments. So we do a lot of work in defense and security, but equally we've been doing a lot of work in civil infrastructure applications where there are particular challenges to do with operating in difficult environments or solving some really difficult sort of robotics challenges. And the project I'll introduce to you today, Demeter, is certainly one of those. But perhaps before I sort of dive into the project itself, I might try and introduce this idea that I call the digitization dilemma. And hopefully you guys are all kind of familiar with this from your own experiences. But sort of my experience of this is around a car that I almost bought when I was 18 years old. So you know, a friend's dad kind of almost convinced me to buy this car from 1970. I wasn't 18 in 1970. No, this is much later. I think he was really nostalgic for this style of car, and he showed me the engine, and it looked like this. And he said, "Oh, look at that! Like you can get your hands in there. It's amazing." And thankfully, I never bought that car because they're incredibly unreliable. And it's a good thing that you've got this much access to all the different systems, because you know you really do need it when you're broken down by the side of the road. But I was just amazed you could see through the engine block, and you could see the ground. You can see all the components that are laid out for you there. You've got the engine block, you've got the transmission underneath. You can see the oil filter, you can see the distributor cap, you can see the air filter. Everything's so really accessible. And so if we fast forward to today, so if you pop the engine on a modern petrol car, or if you pop the bonnet on a modern petrol car, this is pretty much what confronts you. And it's a vastly different picture. We've moved on a lot. I mean, the basics are still the same. So it's still, you know, fuel, air, and spark makes the thing go. But if you look at the number of systems that we've introduced sort of around that, and the way those systems have evolved, it's really incredible. And you know, the auto industry hasn't done this just for the hell of it. They've done it because They've sought better performance. They've sought cleaner engines. They've sought better reliability overall for their customers. They're always competing. And so this is the solution that they've come up with. And basically, it's a really good example of digitization. So if you look at, do you remember the days when you had to like tune your cars? Like this used to be a thing. Like my first car, I still had to kind of tune it. It means you had to kind of twiddle the distributor cap and just get the timing just right, just so that the cylinders would fire at the right time. Well, these days it's all electronic ignition, and that relies on a sensor feeding data back into the system. And if you look at a modern car, there are sensors all through that system, and there's data flowing back and forth. And it's a really good example of digitization. And the performance of engines these days is that much better. But here's the dilemma. So if I were to tell you that half of all calls to a mechanic these days involve a faulty sensor rather than a faulty mechanism, you'd believe me, right? Like it's kind of plausible. You shouldn't. It's like a completely made up statistic that I've just sort of made up on the spot. But actually, it's believable because we've all had that experience of, a warning light goes on our dash. We take it into the mechanic, and the mechanic says, "Oh yeah, I'll just change the sensor, 150 pounds, please." And we kind of grumble about it because there is an overhead. There is a cost to digitization. We're introducing new failure modes and new ways of things going wrong. But we know deep down that actually we're much better off. It's much better to have the catalytic converter sensor drop dead rather than that sensor not being there and the actual catalytic converter failing undetected. So we know that we can improve our systems with digitization, but it's not trivial, and there is an overhead to doing that. And the same is true, and perhaps especially true in the subsea environment. So we know we can do better with modern technology. We know we can digitize our infrastructure and improve the way we maintain that infrastructure and even the way we operate that infrastructure in real time. But we also know that there are sort of significant costs and significant sort of potential things or issues that will arise from doing that. And that's where the challenge is, I think, in digitizing, especially in a harsh environment like this. So if we look at, one thing that we may wish to do, so if we have some infrastructure in the subsea environment, wouldn't it be really great if we could get some feedback from that infrastructure so that instead of kind of guessing blindly or doing really expensive, unnecessary interventions, actually we can use sensor data to inform our decision making, and we can sort of make better, more economical decisions that help us run our infrastructure much more efficiently. So we may want to introduce sensors, and those could be fixed sensors on the infrastructure, or equally they could be carried by platforms that we send down to inspect the infrastructure. But all sensors have some basic needs, and so the first of those is power. You need at least some power to run a sensor. And the second of those is this sensor is going to produce data. And potentially, if you're tracking some high rate processes and you're leaving the sensor there for any significant period of time, that can be large amounts of data that you're potentially generating. And unlike your car, where it's very easy just to siphon power off and connect to a CAN network to get the data back, in the subsea environment, that's actually really, really challenging. So you're putting infrastructure into a very harsh environment, and now you're going to put sensors down there, and they have to operate in that harsh environment too, and they have these needs to kind of be connected to the rest of the world. So an obvious step to do would be just add more infrastructure. So we'll add more infrastructure to support these sensors. So we'll provide power lines that we can run back to shore or wherever, and we'll provide some data lines, and everything's hunky dory. But at this point, like I said, you're going into a harsh environment and you're worried about your infrastructure deteriorating in that environment. And now you're really just increasing the failure surface of your entire system, because now the sensors that you're relying on, they can also fail if they lose power or if there's an issue with the data connection, etc. And so if you take this to the extreme, you could end up with turtles all the way down. So it's just a way of saying infinite regress, like, we could add more sensors to the sensor infrastructure, etc. But it's that kind of situation. And in extremis, there's a lot of really good work going on at the moment looking at things like resident robotics. So the idea is that you put some infrastructure down, so you invest. So when you put something down on the sea floor, for example, you would invest in also putting down this sort of meta infrastructure to support a fleet of robots that might then be used on demand to go and do sort of teleoperation jobs. So they could flip valves for you. They could inspect structures and do all this kind of stuff. And there's some pretty serious work sort of going on in this area. But it's all premised on this idea that you would actually have to make that separate investment in infrastructure. And like I said, that's not cost-free. So a question then is, if we look at, for example, just the sensor data, so assuming we could, say, solve the power issue with things like, batteries and that kind of stuff, but the data is really tricky, and getting that back through the subsea environment is not trivial. And we don't really have solutions that are good for sort of high quantities of data that we can transmit at low power through the water column. It's just not the same as the air environment, where radio communication is really cheap and high bandwidth. And so the question then becomes, well, if you had no infrastructure, could you still get this data back so from the subsea environment? And if you look on Wikipedia, and as I sadly do sometimes of an evening, you come across some really interesting stuff. So this is an example here of one such solution. So this is IP over avian carriers. And so this was actually an April Fool's joke from 1990, where some standards body decided they'd write an actual standard for IP over avian carriers. So that's sort of internet traffic carried by homing pigeons, effectively. And you have a good laugh, and you think, well, that's that's pretty neat. Someone's got too much time on their hands. But then, if you keep reading the article, it turns out that if the conditions are right, this is not such a crazy idea. So guys who take people on rafting trips down rivers, apparently they use homing pigeons. So they'll take all their GoPro footage, they'll take all the SD cards, strap them to a pigeon, and send them back to the tour operator, so they can basically post all that stuff to Facebook without having any connectivity whatsoever. And so this is a this is a thing, apparently. And a couple of people have sort of made sort of joke experiments where they sort of competed with local ADSL providers and actually showed that carrier pigeons were actually by far much higher bandwidth than sort of ADSL lines. So I think under the right conditions, this kind of thing has its place. If we look at the subsea environment, though, our pigeons look very different. So one of the ways of getting data back from some of these sensors is to send people down. So we send divers down. Now that guy's holding a grinder. That's just a stock image, but the point here is that to send a person like that down into the subsea environment, you need a lot of equipment to keep them safe, and you also need a team of people really to keep that person safe. So it's not a trivial thing to do that. It's expensive and it's high risk. We can avoid some of that risk by using conventional robotics. So ROVs, for example, can go down there, and we can design our sensors to be very easy to use by ROVs, by sort of accommodating their manipulators, and so we can get the SD cards back in a way that the ROV can kind of handle. So we can do all of that and engineer that into our systems. But ultimately, if we look at what our pigeon looks like these days, it's a very large, slow, expensive pigeon because of the support that those systems need. So the tip of the iceberg really is the diver or the ROV down there, getting that SD card back, getting the data off the sensor, maybe replacing the battery, maintaining the sensor. But in order to do that, we need a very sort of large investment in a vessel that costs tens of thousands of pounds per day. And because of the logistics of this, we probably can't get our data at a higher frequency than, say, 2 to 3 years. So if we're doing sort of condition monitoring of a structure, we have to wait 2 to 3 years for data for us to act on. So coming at this, if we refine our question a little bit, if we say, well, data without more infrastructure, without sort of high operational costs, without the high safety risk if you're using divers, and without that high latency of just getting the data every 2 to 3 years, really what you need is a better pigeon. We need a better method of interacting with our sensing infrastructure that's under the water with our sensors. And you can see where this is going. So, I said at the outset, we're a robotics company. So to us, robots are an obvious solution candidate. But really, this is potentially a very tough problem to go and do this repeatedly and reliably. Because anytime you replace a system that's either teleoperated or a system that's a person actually physically doing a job, there are lots of things that you take for granted in those systems that are really hard to replicate in an autonomous robotic system. So can it be done? So if we look at the state of play, so I'd say like the past 15 years have been a really exciting time in ocean robotics. So we sort of have a lot of new developments sort of coming along. So we have got our sort of mainstay system. So ROVs like this one have been around for a long time. We know and love them. So these guys operate on a tether, so they draw all their sort of power and communicate all their data via a tether back to a ship. But what that means is we can teleoperate these systems, so we can have a human sort of literally remote controlling these sort of behind a screen. We can use manipulators. We've got 6 degrees of freedom in these systems. So all of that stuff operating in the underwater environment that is sort of well-trodden ground. And these are really sort of workhorses of the subsea environment. The tether is a limitation, but we can get around that. So AUVs have also been around for a long time. So these are autonomous underwater vehicles. So these are off the tether, so they're sort of battery powered. And you know, the example here is torpedo shaped, because a lot of the early missions were sort of simpler missions, things like doing surveys and that kind of stuff. But we also have now a lot of sort of hovering AUVs, which look a little bit more like ROVs. And so we are moving into that space. But the point is that the fundamental technologies, the navigation, the control, the sensing, the low bandwidth communication, all of that kind of stuff is also well-trodden ground. So we've got some good enablers from sort of the traditional underwater robotics domain. But what's really exciting sort of about the past 15 years is that we've seen a proliferation of energy harvesting systems. And so around 2010, this system came out. It may be familiar to some of you. This is called a wave glider. This was developed by a US startup, which was later acquired by Boeing. And what you can see on the right there is this sort of funny looking array of sort of yellow fins, if you like. These are called flapping foils. And basically what this system does, you put it in the water and those flapping foils go down on a tether. And basically as the waves move along and excite the bit that stays floating on the top, those foils are excited and that generates a propulsive force. So this system uses 100% wave energy to get around. And okay, it moves around at sort of a slow walking pace, but actually it has the endurance to cross oceans. So this thing will easily cross the Pacific Ocean. It'll easily cross the Atlantic. It can stay out in the water for 12 months. Its really only limit is biofouling, sort of strangely enough. So it's got an infinite supply of energy, but when stuff starts to grow in it, things get more difficult. But really, it's an example of what could be achieved with energy harvesting. So it uses wave propulsion to get around, and then it uses solar power to power all of its onboard systems. So all of the sensors that it carries as payload, its communication system, its control system, that's all powered by solar. But it is a surface-bound system, so it stays on the surface at all times. Similar conceptually, I guess, but a different sort of approach is a thing called the sail drone. This emerged a few years ago, and this uses sort of the tried and tested method of maritime propulsion. It uses wind power, basically to move around on the surface. And then like the wave glider, it also uses solar power to power all of its onboard systems, control system, etc. But that's another approach. But again, a surface-bound platform, so designed to cover large distances and basically stay on the surface at all times. And then a final example, this is sort of a shorter endurance system. This is designed for duties like bathymetric survey. It has a large solar deck to provide power. And then these guys are using a hybrid approach. So they also carry a diesel tank and a small diesel generator. So they can kind of, between those two things, they can kind of extend the endurance and get this thing out to sea for something like 45 days at a time. So some really, really interesting developments. I guess from our perspective, when we're looking at the subsea environment and the potential to start sort of interacting and servicing sensors without introducing more infrastructure subsea, we really want to be able to bring all of that free energy and utilize the radio communication channels that are available, whether that's to fixed infrastructure or to SATCOMs, that's all available at the surface, but bring all of that down to where it's needed so that we can go and interact with the sensors. We can, for example, provide them with power that we harvest or energy that we harvest, and we can also retrieve the data and potentially analyze it. And so that's the challenge. And that kind of brings us on to the Demeter project then. So I think Graham did a good introduction to the genesis of this in terms of the competition. So I won't dwell on that, but I guess it's worth pointing out the exam question here was, how do we make persistent, trusted, uncrewed operations the standard approach in a whole range of different areas? So I'd say subsea robotics has been characterized mostly by, I'd say, teleoperated systems like ROVs, or short duration autonomous systems like AUVs. But it's a real challenge then to think about how you take those technologies which have their limitations and turn them into persistent, trusted, uncrewed systems. And that's really what we took to heart in formulating Demeter. Our application area is offshore wind. So, in the UK, in terms of a home market, we couldn't really ask for a better environment. So the UK has fully 1/3 of Europe's offshore wind resource, and I'm sure a lot of you are much more familiar with the dynamics of this sector. But what's really interesting is that UK government has committed to a 5-fold increase now in installed capacity. So that's 50 gigawatts by 2030. And when I read this, I sort of did a double take, because I seem to remember reading that there's a 4-fold increase, somewhere around 2020 by 2030. But this was just last year. They've recommitted. So that's a phenomenal sort of increase in offshore capacity, and that's a lot of infrastructure that's going to be going in around the UK. This is what a typical wind farm looks like. So it can be a large array of turbines, sort of arranged something like this, typically installed on a sandbank. So you can see some of the sandbank sort of poking through the water there. That's relevant because, unlike a deep sea environment where, okay, it's high pressure, but not much else happens, on a sandbank, things are very active. So we get tidal flows coming through here. We may get some sediment transport. It's not necessarily the friendliest of environments for underwater robotics. And if you look at sort of a single turbine monopile sort of going into the ground there, you'll see an example of an intra-array cable. And so in a lot of cases, turbines are kind of daisy-chained together like the old-style Christmas lights by a bunch of cables, and then those go into larger cables, and then eventually that's transported back to shore. But these intra-array cables are a really interesting potential failure point, because just like your old-style Christmas lights, if one bulb goes, you can lose the lot. So any sort of break to this chain of cables can potentially cost tens of millions of pounds. So there's a really high payoff to actually digitizing this asset and understanding it, because in this environment, that little junction of cable, so between the base of the monopile, you can kind of see a little junction coming down, running down to the sand, and then eventually getting buried. And usually they'll dump rocks on the buried section, so that stuff is well protected. But the little section that kind of joins up to the monopile, that's actually moving around all the time under the action of currents. And cables have a limited fatigue life. And so you ideally want to know, what's happening to your cable. The flow around a turbine monopile can be quite complex, so you don't always know what's going on. And then when you know that you've reached a certain fatigue life, you want to schedule your maintenance then. You don't want to kind of do it unnecessarily, because it's very expensive to get the work done. So there's a high payoff to instrumenting that. And Demeter, initially, we're targeting this application. So autonomous devices, we partnered with Subsea Insight, who specialize in the on-cable sensing, as well as other companies, Signaloid, who are doing processing hardware, D-Risk, who are specialists in safety critical software development. And then we're getting various levels of technical support from Strathclyde University, Royal Holloway, looking at planning, and Manchester. Just in the interest of time, I'll try and move things on a little bit and make sure there's plenty of time left for questions. But I'll give you sort of an overview of the Demeter system. So Demeter is basically, it's a long-term resident system. So we stay out on a wind farm, or a number of wind farms can be covered by one system. It's infrastructure free, so the robots are wave and solar powered, and they use radio communications. They have a high degree of autonomy, so they're tasked at a very high level by an operator, but they stay out in the environment over a period of 12 months, basically autonomously meeting a data collection schedule unless told otherwise. And really, our whole aim is to enable more frequent, cost-effective, and safe access to the subsea sensors and their data than you would otherwise get with that sort of old, slow, heavy pigeon, a diving support vessel, divers, ROVs, etc. And the great thing is the upfront investment in terms of infrastructure is very low. So the way the system works, so we combine sort of wave propulsion with solar power. So we have a novel wave propulsion technology that enables us to not expend any energy in terms of transitioning between different monopiles or transitioning between different arrays if we're covering multiple arrays. And so whilst we're on the surface, we can use GPS basically to follow a plan that takes us to different monopiles at different times. And then we dive down. So our system is capable of operating subsurface. We dive down, we operate as a hovering AUV. We locate the sensors that are on the cable, and using a variety of sensors, we dock with the sensor. We use low power, high bandwidth, short range communication to interact with the sensor. So we get all of the data off, and that's gigabytes of data at a time. We then process that data on board using our harvested energy. And then we use satellite communication when we're back at the service to basically just transmit sort of key performance parameters. So instead of getting all the accelerations, we would summarize that data, for example, into histograms and send that over as needed. And that then supports operational decision making. I won't. I'll just skip that slide. It was just listing sort of partners and their sort of contribution areas to the project. But please do get in touch with me if you want any more information about the project. We do have 7 partners in the consortium. I'll just bring that up on screen very briefly. We do have 7 partners in the consortium looking at lots of different areas. So those renders that you saw previously, they make the problem look really sort of simple in nice clean water. But actually, to do that for real, it involves a lot of engineering work and quite some novel technologies being put together for the first time. And so we actually have such a large consortium for that reason. We're covering a lot of technical ground in this project. And just some examples of things that we've been doing. So this is our wave energy harvesting technology, which is being validated in a wave tank at the University of Strathclyde. So they've done a lot of work looking at optimizing that geometry and then running experiments sort of in the wave tank to really characterize it and sort of thrash out its performance against different wave conditions. It's been some of our partners have been looking at the autonomy piece. So the sort of current way in which some robotic systems are operated really involves a human defining a task, a planning algorithm developing a plan, and that plan then being fed to the robotic system. And then invariably something in the environment, because the dynamic environment is not as assumed, the robot raises an exception and then looks back to the human to give the robot a new plan. In Demeter, we can't do that. So our robots are out of communication for long periods of time, and we don't want to place that burden on the human operator over the long term. And so we do onboard replanning. So the robot senses things that are going on in its environment. It makes its own decisions about what to do. And so this is sort of true autonomy, if you like. But the challenge with that is you also have to be able to guarantee that the robot will never do anything unsafe. And so we have a couple of our partners, so D-Risk and Royal Holloway in particular, looking at the planning piece, and then looking at how you can guarantee that any plan that's sort of generated dynamically by the robot on its own doesn't violate safety constraints. Okay, and just to sort of wrap up, I mean, we've had some really good sort of first milestones in the project. So we've already demonstrated our AUV docking with a sensor in a test tank at Strathclyde. And we've also had tank validation of the energy harvesting technology, and we're producing like really good performance. And what's really exciting now is we have a couple of further milestones coming up as we complete the project. So the first of those are seed trials, where we're taking the energy harvesting demonstrator offshore and letting it perform some specific test missions to demonstrate that capability. And then finally, we're doing a full data retrieval cycle again in the test tank with Demeter, whereby the vehicle starts on the surface, it dives down, it finds the target on-cable sensor, it docks with it, it downloads the data, it processes that data on board, returns to the surface, and then transmits that over the airwaves, sort of really showing the proof of concept of really what we think is going to be the most challenging phase of the vehicle's life cycle. And that's it. So I've just got the prompt that we need to move on to questions. So apologies for running over, but that's the last slide there. And happy to take questions.
Thanks, Ken. Yeah, I was about to jump in and say, come on, pal. Wrap it up.
Oh, sorry. Yeah.
Hey, great background. Thanks very much for that. Great background. It was almost like a great reveal in the end to show us the the final geometry and the like that you'd landed on for Demeter. So that's brilliant. We have 20 minutes of Q&A now, which we'll go for. We have a mic going around, a couple of mics. I can open up to the floor for sure, and we can get going with Ken. Anybody like to kick us off?
Hi, Ken. It's Sakshi from NZTC. Thank you for that presentation. It was very insightful. I've got two short questions, I guess. One is to do with, so the Demeter technology, I guess I'm thinking a risk area is, the point at which the device dives down, collects the data, and is diving back up to then transmit the data. What kind of challenges do you perceive might happen that is there anything that might stop the device going back, coming back up and being able to transmit the data? Because you've kind of got a point of gap in communication or oversight, I suppose. And my second question is, I'll just give you the second one as well. So you described the device to be able to be resident, but what is do you have an idea of how the device might be picked up, or are you working with like uncrewed, the USV providers to be able to pick up these devices and bring them back to shore for maintenance and all this kind of stuff?
Okay.
Thank you.
Great. No, thank you very much. So yeah, the first one with regards to diving, that's definitely the highest risk sort of part of the vehicle's mission. And so the first thing is knowing when to dive. And so that's part of the sort of planning problem. So one of the risks that you have is if you're diving at the wrong phase of the tide cycle or in adverse weather conditions, then potentially you make that thing riskier. So part of the planning algorithm's job is just to pick the right moments to go down and interact with the sensor. And then when we lose communication, you're absolutely right. So that's why it's so critical. Like an AUV that's out of communication in a lot of other missions. It really does have to make its own decisions at that point. So it has to have the sensing and the processing wherewithal to be able to detect failures that occur during that phase of the mission and then take appropriate action. So for example, if it attempts to dock with a sensor, but it's not able to do so, it has to apply a little bit of reasoning to determine what its next action should be, whether that's just to come back and try it another time, or whether it's to persist. And so all of that kind of decision making is encapsulated in the planning module. And that's fine. Like in robotics, we do that kind of thing all the time. But what you mentioned about reliability is absolutely true. And so we also need to be able to verify that the decisions that the system is going to make at any point in time don't lead to unsafe situations for the vehicle. And so that's our route to reliability sort of during this phase of the mission, if you like. Your second question there was about like residents. And so that's an absolutely fair point. So depending on where you're operating, in our waters, we could probably operate for, perhaps up to 12 months before a robot really needs to come back in for servicing. In warmer waters, that might be a much shorter period. Your point there about recovery is one of the great things about having this wave propulsion technology is that actually, as long as you're patient enough, you can cover vast distances. And so we actually envisage the system being recovered to shore bases rather than requiring any workboats or anything like that to go out and recover systems unless they're sort of seriously in trouble.
Thanks, Ken. Ken, can you just give us an indication of the size of the device?
Yeah, the way I describe it in terms of size and weight is it's like a large washing machine. So if you imagine that kind of scale.
Yeah, great. Anybody else? Yeah. Go for it, Tess.
Hi again, Tessa Scott with the Wahren Catapult. Do you have built-in redundancies, etc. for, obviously there's going to be a lot of vessels floating about these wind farms. I mean, you say it's the size of a large washing machine. How are you taking into account to make sure, for want of a better phrase, it doesn't get run over by a boat?
Yes, so that is absolutely a risk. We're probably less concerned about our system at that point and making sure that the other party is safe. And so there are a number of things. So it's early days for us in terms of proving out the technology. But we are starting to think about that. And so there are different schemes that we can employ. So for example, we can define notified areas where our systems basically stay like a pen, if you like, sort of on the wind farm that's then sort of notified to mariners, where we kind of operate and do our sort of energy harvesting piece. And then the other thing is we might take some more sort of active collision avoidance measures. So we're not going to be particularly fast. So it's very hard for us to sort of follow the coal regs in that respect. But one of the things that we can do, because we're also subsurface capable, is that if we, for example, detect the noise of an engine and it's above a certain threshold, we can, for example, leave the surface for a period of time. So there are measures like that which we've thought about, but which probably aren't within the scope of our project at the moment, while we sort of try and prove the core concepts and the core feasibility of the tech. But it's a really good question.
Thanks. Cheers.
Cheers, Des. I think there's another question at the back there, yeah?
Hi, Ken. Thank you very much for the presentation. Emmanuel from Oceaneering. Thanks for having our ROV footage there. Always appreciated. Thank you for that. Yeah, just a quick one. What is the vision of the commercial model or the strategy approach? Is this more with wind farm owners or with IMR contractors? Ourselves could be one. What's kind of the approach to put the system to market and what timeline are you looking at as well, please?
Yeah, so for sure. So basically, this year we're sort of proving technology, and we'd like to be able to do some early trials. We're quite agnostic in terms of how those early trials and pilots are conducted. So whether they're conducted through companies like yourselves or directly with owner operators, we're quite agnostic. The key thing we look for there is getting early validation and data. Longer term, we're talking perhaps 2 years down the line. We would look to form relationships, I think, with companies like yourself, who have got sort of reach and market presence already, because obviously we're a small company ourselves. So we're definitely open to having those conversations, but I'd be lying if I said we had a very sort of concrete strategy that we would stick with. So we're still proving out the tech, and keeping an eye on commercialization and not at this stage wishing to sort of close off any different channels.
Thank you, and happy to connect later on, Ken. Thank you for that.
Great.
Great. Yeah, there's been a number of fascinating things on this project for me, Ken, from the different geometries that have been tested for the wave harvesting, but perhaps just while other folk think of a question, just on the power side, this obviously isn't like a megawatt powered device. Can you give us a high level overview of the sort of how the power management has been sorted?
Yeah, so I guess one of the interesting things about these systems is so that there's sort of power and there's energy, if you like, and so we get a reasonable sort of level of power, sort of certainly at peak conditions with our sort of solar panel approach. But the thing that you're always trading off is time. So we're not necessarily a low power system. So when we're operating as a floating AUV, we draw a considerable amount of power. But what we're really doing is we're consuming energy at a certain rate, and that energy is also accumulated at a certain rate when we're on the surface. And so what you're really trading off is the amount of energy that you expend under the water versus the amount of time that you need to spend above the water. And actually in our application, to compete with a diving support vessel that comes through every 2 to 3 years and gets you your data, actually you don't need very much time to enable you to perform that mission. So we can harvest energy over a period of a few days and go down. And whilst we're doing that, we're traveling for free using wave power. So it's quite an efficient and I guess surprising conclusion. But we can have bursts of very high power. We're probably no different to an ROV or a hovering AUV in that phase. It just happens that phase of the system's life cycle is a small portion of the duty cycle, if you like.
Yeah, copy there. Do you have any numbers off the top of your head?
So probably not that I'd like to share at this point until we have a bit more certainty. One of the reasons we're going to sea trials is just to validate some of those things. So I wouldn't want to put those out there until we know for sure.
Copy there, Ken.
Yeah.
Anybody else? Make it happen.
Phil Gordon, CGI. Sorry.
No, go for it, Phil. Go for it.
So I've got a couple of questions. So these device, your robot device, how long would you envisage it would stay at like a one wind farm? Is it going to be would it be permanently resident and continually checking it, or would it be there for you know, a month and then go to another wind farm. So just interested in that. Interested in, you know, in terms of the resilience of the wind farms and thinking about the ecosystem, and, you know, would you see that there would be a, you know, an array of equipment like drones, and you'd work in partnership maybe with drone technology? Could you consider drone technology as part of that ecosystem? Yeah, so, and maybe one other question, how deep can it go? Thank you.
Okay, great. So three questions there. I'll try. I've just jotted down bullet points. You may need to remind me. Okay, so in terms of the question about servicing, say, multiple wind farms, so really it's going to be a very flexible solution. So it's really going to depend on the customer's data capturing needs. So, for example, if, you know, depending on how frequently they need to capture data and how large their individual arrays are, and how many vehicles they want to invest in, really we could configure the planner to handle or to produce schedules that kind of optimize there. And so our systems are not tethered because they're not reliant on any infrastructure, so they'll happily sort of cross an ocean and service a wind farm on the other side. You may just have to wait several months for it to do that. So in theory, we can come up with very tailored arrangements for whatever our customers kind of need. And so that's one of the great strengths of not being tied to any particular infrastructure that the customers have to install. And those plans can then be changed. So if a customer decides they've got some assets that are at higher risk and they want them to be inspected more frequently, that can be done as well. I hope that answers your question. In terms of using this as a platform for an ecosystem of robots, I guess you mentioned drones. So it happens that on the defense side of our business, as well as the civil inspection side, we also do a lot in the aerial space. And so we ourselves have got sort of quite a capability when it comes to drones, but likewise, we are always open to collaborating. But that's a really interesting concept as well, because if you have sort of excess power that you're able to harvest, or excess energy, then potentially we could share that with other assets. So we're already thinking about how we share that with sensors, but there's no reason why we couldn't share that with other robotic systems. So it's a really good point. And the other one is sort of how deep. So I'd say at the moment we're targeting sort of the typical depths at which sort of these monopile wind turbines operate. So, you know, probably the depth ratings that we're operating to at the moment are sort of 50 to 100 meters. But we have designed our system specifically to be able to accommodate sort of heavier pressure hulls, which will enable us to go down to the really sort of deep depths, where we're talking thousands of meters. But in the first instance, while we're focused on wind, these are going to be shallow water applications. And so depth ratings are not going to be enormous initially. However, our platform has already been designed with that in mind. So when it comes time to put in a very heavy pressure hull, for example, to enable the system to go down, we've already worked out what our CG is going to look like, and we've made sure that our wave propulsion technology will work under those conditions and that kind of thing. So we are thinking ahead to those kinds of applications too.
Thank you.
Thanks, Ken. I think I've got time for one more question. Take it up.
Hi, Ken. My name's Alice Pease, most recently NZTC. Quick question regarding the technology itself, from the use to power the kind of data transfer from the sensors to the Demeter device, and how do you ensure kind of agnostic docking with lots of different types of sensors?
Oh yeah, that's a really good question. So we're coming up with fairly modular architectures for how the system interacts with the sensors. So these are based on short-range communications. I don't want to sort of speak out of turn because one of our partners has kind of got IP in that area. But what I can say is that we are taking a very sort of modular approach. So although, you know, we are working with sort of particular types of sensors at the moment that have been sort of designed or adapted to assist with the docking phase, we are taking a very modular approach to be able to make the system kind of more generic, if you like. But at this stage, yeah, I wouldn't like to kind of tread on our partners' toes there and reveal too much about the technology that's being used.
Good. Cheers, Ken. Thanks, Alice. I think we're going to wrap it up there. Maybe a final question for you, Ken. you know, we're looking at first deployment here, our first field trial testing in the summer, which is great. It's a sweet spot for NZTC. Any idea yet where you're sticking this in the water? Can you give
Yeah,
give the
so
crowd here a
we'll very
indication?
likely be offshore Blythe.
Offshore Blythe.
Yeah.
Did you say? Yeah. Okay.
Yeah, that's right.
Northeast
that's right.
England. So happy days. So at least we know what will be happening in the summer. Hey, that's us. You know, Ken, thank you very much. I think we can. I give Ken a wee round of applause. You might see it and make you happy. That was really good, Ken, and hopefully catch up. I'll see you on Friday at the quarterly meeting. We need to vacate the room now, everyone. Time to get out. You can carry on some of the conversations upstairs in reception, but thanks again for making it along. Been a great audience. Cheers.